Today I'm going to be talking to you about computational thinking. I'll get into what exactly it is and why I think it's so important. So before we really get started, I'd like to start off with a problem. So you see this 10 by 10 grid up here. Simple question, how many squares can you draw on this grid such that all four vertices of the square are points on the lattice? So one example of a square would be this, another example would be this. Any size is fine as long as the four corners are on the lattice. So why don't you guys discuss this amongst yourselves a little bit, think about it, and maybe in 1 or 2 minutes I'll ask for some ideas.
Can they overlap?
Yeah, the squares can overlap. They can be any squares you want.
So what was the question? How many squares?
How many squares can you draw such that all four of the corners of the square are one of those points?
And they can overlay.
Yeah, they can all overlap. Overlapping doesn't matter. They're all separate.
10 to the degree of 10.
10 to the degree of 10. Okay, that's one guess. I'm not necessarily looking for an answer. It's more of a way to get to the answer, say an algorithm to get to the answer. All right. Does anyone have any ideas? 101, okay.
To break down one problem into 7, 10, 8.
Okay. What was your idea?
The sigma of selection of n from 10 and the n going to be from 1 to 10.
That's on the right track. Okay, you're not quite, but you're basically right. It's minor. You guys are all going for the answers. I'm just looking for a way to get started with this problem. I don't need the answer right away.
You should multiply n by n divided by 2 and sigma from 1 to the number of n.
All right, you two are both very close, but not quite right. All right, yeah. So you all are going towards answers and formulas, and I get that. But really, if I'm just asking for a number and you're looking at this 10 by 10 grid, it's really hard to think of an answer because there's so many squares. The square is so big. So the fact that the grid is so big really blocks your brain from trying to find patterns and trying to look at it from an objective point of view. So the main way to solve these kinds of problems, especially this one right here, is to start with small cases, right? And then from those small cases, we can figure out patterns that we can finally go back to this big case. So if we look at this, some smaller cases, on a 1 by 1 grid, how many squares are there? Just one, right? One, it's just that square. On the 2 by 2 grid, how many squares are there? 5. Most people remember these 4, but they forget the big 5th one. So there are different sizes of squares too. That's an interesting observation. On the 3 by 3 grid, we have 9 of these small squares, 4 of the bigger ones, and 1 of the biggest one. And on the 4 by 4 grid, I'm not going to draw them all, but again, there are 16 of the smallest ones, 9 of the 2 by 2s, 4 of the 3 by 3s, and 1 of the 4 by 4s. So now that we have these small cases, let's start looking for some patterns. Do we see a pattern? I think there is some pattern that's very easy to see right here. Right? Because you have 1, and then you have 4, 1, and then 9, 4, 1. So it's always the same as the one above it, except you have another number added to it. So if you put it like this, and no matter what the grid size n by n is, you're going to have one large square that's size n by n. We can call it a size n square. Then we have 4 of size n minus 1 by n minus 1, 9 of the next smaller, and 16 of the next smaller, and so on and so forth, until you get to 1 by 1. This is the pattern that we see, and I think it's reasonable to assume it works for any size of a grid. So another thing is that these numbers aren't just random numbers. 1 is 1 times 1, 4 is 2 times 2, 9 is 3 times 3, and 16 is 4 by 4. So it's also reasonable to assume that the pattern will continue. So now we can just go back and use this pattern to fill out the rest of the boxes for the 10 by 10 table if we look at it by sizes. So we have 1, 4, 9, 16, 25, 39, blah, blah, blah. And then if we add all these numbers up, we get 385. What you two were saying about the generalizing it for n by n is very good, because obviously it's not just the 10 by 10 that we care about, it's any n by n grid we care about. And this pattern would work. So it would be the sigma from 1 to n, right, from 1 to 10 in this case, of n times n. So it's not sigma of 1 to n times sigma of 1 to n, it's a sigma of 1 squared to n squared. Okay, cool. So let's take a step back from this. Oh, my bad. Let's ignore that, what we just saw. Are there any more squares? Yeah, we forgot about them. Diagonal squares, right? We didn't think outside the box enough. Remember, I was very clear about this. The only restriction is that the 4 corners of the square have to be on the grid, right? So this square, the 4 corners, are the points on the grid, but it's just diagonal. So the lesson here is that you have to be creative. You have to think outside the box. Not always everything you think about is every possible solution to the problem. Okay, so that was just a fun little problem to get started, to get your brains thinking. Let's take a step back, talk a little bit about myself. Hi, my name is Shaya. Shaya Zarkesh. I am currently 15. I'll be 16 in 2 days. And I like math a lot. Ever since first grade, when I went with the kids a year older than me in math has always really been my specialty. And I've always studied it a lot. I still do things like math competitions. So math is like kind of my life. So last year, I co-founded a startup called Polyup, along with Yahya Tabesh, which I'm sure a lot of you know, and I think he might be in here right now. Yahya Tabesh. And along with my father, Amir Zarkesh, right there, and Shaheen Hedayat, who is our CEO right now. He's not here with us. And this startup is not quite about math. It's about teaching computational thinking, which is heavily intertwined with math. So today I'm here to show you, again, what computational thinking is and why it's so important. Okay, so a little bit about our team, if you were wondering, just really quick. We have Shaheen Hedayat, who is our CEO, sorry. And we have Yahya Tabesh, who is basically our main content generator. Yahya has 30 years of math experience in Iran. At Shaya University, he's taught thousands of students. Basically, any Iranian you know will know Yahya Tabesh. He is that famous. So he really knows what he's doing. He's been doing it for so long. And he's very passionate about math education. We also have my dad, Amir Zarkesh, who takes more of a managerial role in the company. And we have Zohre Alahian, who is right there. And she is on the board of directors and helps give advice to the company. And we have Morris Michael, who is a UI UX designer with over 90 million gameplays. He is helping us on our game, which I'll talk about in a second. And lastly, we have me. I mostly work on coding the mini games that I'll talk about in a second. And I also give feedback on the UI and UX of our products. Because, of course, our target market is teenagers like myself. So I think that's really cool. My bad, other way. OK, so what do we do at Polyup? We do basically 3 things. The first thing is computational thinking workshops. The picture you see right here was in the same room as you are right now. We held a computational thinking workshop for high schoolers in the Bay Area. And at these workshops, Yahya helps teach them, or not really teach them, helps guide them through computational thinking problems and helps them acquire computational thinking skills. But the problem is, even though Yahya has taught a lot of students, he cannot teach every student in the world, no matter how good of a teacher he is. Just, you can't go to every student in the world and teach them. So how do we fix this? And the way we have fixed this, the way we have fixed this is by implementing a version of Yahya, which we call Yahya as a chatbot, in our computational thinking quests. And these quests are basically a series of problems where a player can explore a specific problem, just like the one I showed you. Square Hunt is an example. Can explore them by themselves, and then Yahya will give them adequate advice based on how they're doing in the problem. If they are completely off track, Yahya will help bring them back on track. It's a deterministic chatbot that depends on what kinds of responses you give him and what you do in the game. And the other thing we do is, the problem with this is that, great, now we have an ability to teach all the students, but now we need to spark interest in the students. I mean, I know me and my friends aren't just going to go to some random site and play math games for fun. I mean, we're done with school, it's summer right now. So how do we spark interest in students to actually learn and come to our site themselves? and that's through a game. We call this a social simulator game, and it involves becoming as popular as you can on our fake social network. So we think it'll really resonate with users. They're going to affect what kinds of things they post to basically pander to their population in every particular region and basically take over their world with social media. So it would really resonate with me, and I think it would really resonate with a lot of teenagers. So these are basically the 3 things we do at Polyup. Okay, so now let's go back to the square exercise I gave you at the beginning, the warm-up problem, right? What was the point of that square exercise? Well, it's a great example of a computational thinking problem. It has every aspect of a computational thinking problem in it. First, decomposition. You have to take the problem, remember the 10 by 10 grid, and look at smaller cases, the 1 by 1 grid. And another way we decompose it is by looking at the various sizes of the squares, such as the 1 by 1, the 2 by 2, the 3 by 3 squares on the smaller grids. The next thing you have to do is pattern recognition. This is probably the hardest and most important step. How to recognize patterns inside these numbers that you see. Remember, we saw 1, 1, 4, 1, 4, 9. There's some kind of pattern going on there, and then you realize, oh yeah, it's 1 squared, 2 squared, 3 squared. Next thing you have to do is abstract your pattern. That's where we took the pattern we found for the small cases and applied it to the large case, the 10 by 10 grid. And that's how we found our answer. And after you do all that, you can do something called algorithm design, where you basically did what these 2 gentlemen and lady did right now, where they took it and basically said, let's do it for any n by n grid, and design an algorithm for how a computer can find it. And that's going to be with the 1 times 1 plus 2 times 2 all the way to n times n. And overall, creativity encompasses all of these steps in problem solving. Because remember, we didn't really think about all of the squares, so at the end, we got the problem wrong because there's also diagonal squares. Cool, so a little bit more about computational thinking as a holistic view of it. It's like critical thinking, but instead of with words, where you have to read the words and analyze them for their meaning, it's more with numbers, where you have to look at numbers and problems, complex problems, and analyze them for possible solutions and patterns in them. It's not really the math you learn in school. So it's not like we're teaching you calculus or we're teaching you logarithms. It's not like a set particular subject. It's more fundamental to that. It is the basis for how you approach anything in math or really problem solving in general. It doesn't even have to be math. Another way to think of it is applying computer science concepts of computer programming to outside computer programming. So basically, what's really important is taking computers and allowing them to solve complex problems for you, because a lot of times these complex problems are too hard for humans to solve themselves. And this is where computational math comes in. Computational thinking is the backbone for computational math, which is a series of mathematical topics that are carried out with computers instead of humans, because again, they're computationally intensive. They include algorithm design, which is, again, what we did right now, designing an algorithm to find the number of squares. Data science, where you take large amounts of data and analyze them with clustering, classification, regression, things like that. Cryptography, taking data and making sure it's transferred securely. And that's with computer-generated functions and hashes and everything like that. We have graph theory, the study of states. We have machine learning, which I'm sure all of you have heard about. And high-tech startups, machine learning is key. We have to program computers to learn for themselves because we can't necessarily teach them as well as they can themselves. We have computational geometry, which is basically what it sounds like, geometry, but computationally. So it's geometry with numbers. And lastly, we have information theory, the study of information, how we can transfer it securely and efficiently. So the basis for all of these topics, which a lot of them are the basis for a lot of startups and what a lot of startups are working on, is all computational thinking. It's all about how to get computers to do what you want and how to solve complex problems by breaking them down, recognizing patterns, and putting them back together. So why should really you care? You might be thinking, okay, yeah, sure, some math thing. But you, as startup entrepreneurs, why should you care about this thing called computational thinking? Well, I think Carnegie Mellon puts it best, why it matters for everyone. Computational thinking is a way of solving problems, designing systems, and understanding human behavior that draws on concepts fundamental to computer science. To flourish in today's world, computational thinking has to be a fundamental part of the way people think and understand the world. So today I'm trying to prove to you why computational thinking is essential for you to create a successful startup. So first, some general points for why this is true. First, startups, the entire point of a startup is to solve problems. And the entire point of computational thinking is to solve problems. So it might be a little bit cliche, but definitely the mindset you're using in a startup and the mindset you're using in computational thinking is very similar. Second, startups aren't big. They're usually 2 to 3 people large, right? You can't just think, oh, someone else will do all the mathy stuff for me, and I'll just manage them. Nowadays, because startups are so small, you have to look at all aspects of the startup. And that includes the mathy stuff. That includes the computational stuff. And you have to actually do these calculations and math for yourself. Lastly, it's interesting little statistics. The most common degree of startup founders is computer science. I got the statistic from Australia, but I assume it's true for many other countries as well. So obviously, computer science and computational thinking heavily intertwined. So it's interesting. There's startup founders are generally very computational thinking oriented people. Sorry. And so that leads you to think, I think computational thinking might be very important for startups. All right, so the first main reason you might need computational thinking is because of research and development. Now, again, since startups aren't very big nowadays, you have to do the R&D for yourself. Sure, big companies might have an entire section for R&D, but since you're a startup entrepreneur, you have to do the research and development yourself. Second of all, computers can't help with this research and development, and you need programming skills to program the computers, especially in high-tech entrepreneurship, to get them to solve your problems for you. Lastly, there's a lot of about money. What kind of product will sell the best? All of these rely on models and data science, looking at profit margins and quality versus price, and seeing what will sell the best and give your company the best profit. And this all relies on computational thinking and data science. Cool, so a great way that we can visualize this is that computational thinking is the foundation for a lot of computational math subjects, data science, cryptography, and discrete math. And at the same time, computational thinking involves problem solving and computer programming. They're basically the 2 pillars of computational thinking. These are the subjects that computational thinking feeds into. And for each of these 3 subjects, there are startup solutions that are happening right now and are very popular. Again, for data science, it leads to machine learning. Cryptography leads to security solutions, and discrete math leads to information theory, which are all really useful for high-tech startups. And this is all when you integrate problem solving and computer programming into the computational math subjects. Cool, so the next reason is finances. How much money do you have and how will you use it accordingly, right? You need computational thinking to look at these solutions because you need a sense, you need basically number sense, which this is what I call it. It's basically being good at estimating how much money things take. And that is very important, that is very crucial. That's a crucial application of computational thinking. Just being comfortable with numbers and allowing yourself to do these complex problems of finance in your company, breaking them down into the specific sectors, finding patterns in these sectors from other companies, and applying them for your own uses. Also, again, the ability to make accurate estimates relies on computational thinking. So again, it's important in a lot of sectors of startups. Cool. Lastly, I want to just mention pattern recognition. The most important part of computational thinking, I'd say, is pattern recognition, the ability to see patterns in numbers. But this, conceptually, it's just numbers. But with the mindset you are in, practically, it allows you to be better at pattern recognition in general day-to-day life. Say you're working at a company and you go to an investor, and they say they respond negatively to some part of your presentation, your pitch presentation. If this happens with a couple investors, you need to pattern recognition to notice that, oh, we should probably change this part of the presentation. Sure, it's a little bit of a hand-wavy example, but the mindset is basically the same. You need to recognize patterns, and that is crucial for making correct decisions in your startup. I'm sorry. Cool. Lastly, we have software development and coding. Obviously, since all of you are high-tech entrepreneurs, coding and software development is crucial. So the problem right now with coding is that schools really only teach you syntax. They tell you, okay, here's Java, here's a for loop, here's an if statement. Here's how you create a functional program in Java. But they don't really tell you, how do you solve the problems? How do you solve complex problems with Java programming? They just give you the tools you need to learn how to get good at that. And getting good at that is computational thinking. Coders, again, lack ability to solve problems on their own without assistance a lot of the times. What really differentiates an amazing coder and an average coder isn't their knowledge of the programs, it's their ability to take big problems and solve them on their own. And again, the ability to modify and apply existing algorithms is a crucial part of any coding. And algorithms are a huge part of computational thinking, again, because of their efficiency and correctness. So again, modifying an existing algorithms is huge. Computational thinking leads you to algorithms. So computational thinking is essential for software development and coding as a whole. All right, so I've given you a lot of reasons why, but I haven't really told you why you can get better. You might be thinking, oh yeah, this is a set inherent ability to solve problems. But no, that's not true. Computational thinking can't really be taught in the same sense that maybe logarithms or calculus can be taught in a class, but it can be learned through experience. So one way to do this is through research projects. I would argue that research projects really boost your computational thinking skills because no one's really telling you what to do. You have a set question, and you have to take data, you have to analyze it, look for patterns in the data, look for anomalies in the data, and then figure out what that means. And that is basically the entire process behind computational thinking. So the next one is to take courses in computational math subjects. Now this isn't just to boost your computational thinking skills. I would argue that these computational math subjects are extremely important to life today. I mean, all the time we're taking problems that we can't solve ourselves and giving them to computers. And this is a lot of what startups do. So taking courses through things like MOOCs, things like Coursera, they have a lot of courses on things like data science, cryptography, information theory. Those would be extremely useful. And again, would help boost your computational thinking skills and make you think more computationally as a whole. And lastly, try Polyup out. This is a little bit of a plug for ourselves, but it would be great if all of you tried our product out. It's geared towards younger children, so people around my age. So you might find the problems easy, but I would bet that the problems we are giving aren't really dependent on age. Things like the square problem, it wasn't an easy problem now, was it? So I would argue that you should try Polyup out. Try our challenges that we have, and that would probably get you into the mindset of computational thinking. And lastly, in case you think we're just some fringe company working on computational thinking, we made all this up, that's not true. It's not just us. There's Carnegie Mellon University is a huge proponent of computational thinking. They have an entire center for computational thinking. They advertise it a ton. So you might want to check that out a little bit. Also Google. You all know Google. Google is a huge proponent of computational thinking again. You can search up their videos about it, and they're all great. Lastly, Stanford. A lot of professors at Stanford have been researching how to adequately instill and measure students' computational thinking skills. And Yahya Tabesh and I have actually instituted a program in Stanford to do just this. Figure out how to measure students' ability in computational thinking, and from that, figure out how to teach them the best way computational thinking skills. So with that, I want to say thank you, ask for questions. Do any of you have any questions? Yes?
Can you tell us a little bit about your challenges? You launched this business when you were how old?
15.
15.
So,
Can you tell us a little bit about your personal experience and some challenges?
right, yeah. Some of the challenges, I think you're referring to me being this young, and I agree. I'm not offended by that. Yeah. Yeah. I mean, my dad really got me into this, and I was really excited to do it. I was working with Yahya Tabesh on this book he was writing about problem solving. So we really wanted to take this to the next level and basically turn it into a company. Personal challenges, just being so young, a lot of times I feel like I am lower status than the other co-founders, if I'm going to be completely honest. And I feel a little bit scared to give my opinion a lot of times. And my entire process, this 11 months I've been in this startup, is basically breaking out of my bubble and being able to give my honest opinion on things, even if it might piss off the other co-founders. So that's one of the main challenges I've had and tried to get out of.
Where did you learn such excellent public speaking skills?
I don't know. I do debate in school. I did debate for a couple years in school. So I think that might have to do with it a little bit. But yeah, I don't know. Yeah.
I also wanted to congratulate you. I haven't seen this great of public speaking and this much confidence and smoothness in conducting your presentation. The question I have for you is that do you feel like you've identified the pain and that people really feel like they want to address? And that's the first question. And the second question is that what's your marketing like? How do you market your product?
The second question I understand very well. First question, are you saying in the context of computational thinking and why we want to teach it to people?
Why would people want to buy your product, or why would people want to choose
Right.
look for you? Let's say
All right.
If I was not in this room today,
Exactly. So this is tying into the second question. So let me answer that first, and let's see if that answers your first question as well. So the way we're marketing this product is actually, again, remember how I said if we just put the challenges up online, honestly, I don't think it would get a lot of traction. I mean, no one wants to do math on their own. So what we do is we have a game, and we think this game is really attractive to teenagers my age. I think I can speak for myself here. I would be very interested in such a concept of a game with a social simulator. And this contains the challenges. I'm sorry, I might have forgotten to mention that. But it contains these challenges. So when you're playing the game, you can actually go and do these challenges. And this will give you some booster, some incentive in the game. So it gives you kind of an artificial incentive to work on these problems. But even if the incentive is artificial, we're fine with that because we're boosting students' computational thinking skills, which really is our mission statement. As far as your first question of the pain, we see more of a lack of skill in the industry, especially in a computer science sense. As I was saying, in schools, students are learning the syntax or how to write in Java, how to write in C#, but they're not really learning what computer science is for, which is working on these big projects, which are basically big problems that they have to solve. So it's more of a lack in the industry that we see rather than a lack individually. Yes?
So I love how you explain why math is so important, and I remember being in school and never understanding why
Sure.
we had to take math.
Right.
I wonder, are you working with different schools, integrating games more into the curriculum, or how are you working with
Yeah. That's another great question. We actually held a workshop at my school, the Harker School. So we held one there, and we basically showed them our products, our challenges, their quests now. And we also showed them some computational thinking problems, and they were really excited about it, which was nice. It didn't seem like it was just a math class where everyone was falling asleep. They were really excited about the problems. So we're hoping to bring these workshops to other schools as well. But more of a long-term thing, what we hope to do is take these challenges, basically put them in a box and provide them as materials to schools. But the reason we're not doing that right now is because schools are really late to adopt these new techie things. So we have to basically prove ourselves in the market first, show them that we're actually doing something, show them that we actually improved students' computational thinking skills, and that has to do with measurement capabilities. And then we can go to schools with some proof and be like, would you like to implement this in your curriculum? That is, yeah, exactly. That's a huge part of what we're doing right now. We're gathering all sorts of data when you play our challenges. So for example, I might, if you all don't mind, I might show you a demo of one of the games right now, where depending on what kind of solution you go for, we can actually basically say, oh, this person's super good at it because they got the solution right away. Things like that. So yeah, data analysis is huge for us. So I'd like to just give you guys a short little demo of one of our games. So let's see. Sorry, I might have closed it before. Okay. All right. So here we have one of our challenges. So you see there's Yaya talking to you, or Yaya, sorry. And you basically reply to his chats. And this problem in particular is you have 8 weights. One of them is lighter than the other ones. So how do you go about using this balance you have to figure out which of those weights is lighter than the other one? One way you could do it is say, if I just guess randomly, or I might get it right. See, depending on what I do in the game, I just randomly took a guess, I was wrong. He asked me, do I want to play another round? Sorry, it's sort of buggy. But sure, I want to play another round. Let's say I do 2 and 2. Let's see if any of these are lighter than the other. Oh, look, it's one of these 2. And I put it back, check. Again, this one's lighter, so this has to be the counterfeit weight. Right, so I basically did it a way, but my way wasn't necessarily the best way to do it, so he's asking me now if I can do it in 3 comparisons every try. So it basically goes through a series of algorithms that can solve this problem. Sorry, did you? Did you want to answer it? Sorry, the answer is just to put 4 on a side, and then the lighter side will have it. 2 on a side, lighter side will have it. 1 on a side, lighter side will have it. Quick question, can anyone think of a way to do it in 2 comparisons? Because what I just said was 3 comparisons.
Yeah. Yes, 3 by 3.
3 by 3. Have you seen this problem before?
Yes.
Okay, cheater. No one gets this on their first try. That seemed a little sketchy. So it's cool, right? Because you explore the problem on your own, and the bot assists you when you need help. And you don't have to ask it for help. It just watches what you're doing. And you really feel a presence while you're playing it. So I think that's really cool. Okay, sorry. That was a little bit of an impromptu demo. But yeah, this is the challenges. All right.
Are you any good at chess?
Not anymore. I played when I was like 5 or 6. Yeah. Is that any relevance to that question? Or just wondering? Okay. All right. Does anyone else have any other questions? Let's see. All right. Is that all? Cool. Thank you.